Chat.
Thanks.
Welcome back to our book club for analyzing baseball data with our third edition. We are now headed into some of the baseball topics after spending a few wonderful weeks talking about R and the data sets that we have in front of us. As you can see, chapter 4 is about the relation between runs and wins. And I thought what we're to do today via the learning objectives is to introduce some sabermetrics, establish the Pythagorean win-loss formulas, and more generally talk about linear regression models. Our route today, as you can see on the left side of the screen, is in a few sections that mostly follow the textbook. I tend to talk pretty fast, so at any moment, feel free to stop and ask questions. Following the textbook's lead, I wanted to double check and see what the most recent data was in the Lawman package using mostly the same code. In particular, we're starting with the team's data frame, grabbing some columns that we're going to use today. And this in general is a good strategy, especially when you're doing machine learning, to only bring along the columns that you're going to use in the calculations. So here we have the year ID, team ID, franchise ID, number of games, wins, losses, runs scored, and runs allowed. Admittedly, I was a bit saddened to see that the most recent data still comes from 2023, and we are now about a year and a half later. So unfortunately, I'm not going to talk about the year 2024 data. One thing I really wanted to emphasize before we really get into it is that, especially if you're new to talking about baseball statistics, you should be aware that in baseball history, there were some seasons that were shorter than others. Most baseball seasons in the past few decades had 162 games played by each team in each year. And I made this quick visualization to show you that we have a few exceptions. I made these graphs in ggplot following last week's presentation on graphics. For the sake of visual brevity, I've hid the code in these fold down boxes. So if you want to look at the graph code later, you can. But in particular, talking about the baseball history, you may recall that 1981 was a strike shortened season. 1994 was a strike shortened season, and that continued into 1995 when the season started a bit later. 2000 was infamously a pandemic shortened season, but otherwise we could understand that baseball tends to have 162 games per season. When I was building these slides, I just came across a fun fact from Reddit. The Braves, who have 4 championships in their franchise history, have never won a World Series when playing 162 games in a season. Now, you probably remember the Braves winning in 95, but they've also won in, I believe, 21 as well. So when you go back and look at that, you see that's also not a full 162. But to emphasize, we could use our R programming skills, team's data frame, some dplyr verbs to look for the Atlanta Braves and the World Series winners and see that claim at the top of the screen was indeed true. And to finish off that story, in 2021 in particular, there was a game that was rained out. They decided not to make up that game in versus Colorado because it had no playoff implications. Now, the reason I wanted to bring up the shortened season is because when we study baseball statistics, and I'm coming from the point of view as a statistics teacher, I want us to be mindful that we have both what are called count statistics and rate statistics. Count statistics, for example, could include the number of at-bats, number of earned runs, the number of hits, or the number of innings pitched. Whereas rate statistics, as you could imagine, are the ones that are formed by fractions. For example, batting average is a fraction of hits over the number of at-bats, while earned run average, as you can see, is the number of earned runs divided by the number of innings pitched, but that's usually rescaled to a default 9 innings per game. So we might sometimes call that earned runs per 9 innings. But when we are thinking about these statistics, we might have to keep these in mind of these different notions between count statistics and rate statistics. Now, with all that said, let's go ahead and dive into some of the textbook code. With a slight departure from the textbook, I decided to focus on the years starting at 1998 instead of 2000. I leave it up to you if you could guess why I did that. But because I was mostly worried about the number of games in a season, many baseball analysts these days skip the year 2020 just to make some exposition a little bit easier at the beginning. You could see some of the columns that I'm going to grab from the Lawman team's data frame or data table, and we're going to use these variables through this hour. In particular, you notice that we've also have some more custom variables that we tack on to the data frame using the mutate command. Run differential is simply the difference between runs scored and runs allowed, whereas win percentage is the number of wins divided by the number of games played. Out of curiosity, I also wanted to keep track of which teams made the playoffs, but this being in the so-called wild card era, you have to keep track of both division winners and wild card winners, which is available in the Lawman data set. With a slight departure from the textbook, I wanted to focus a little bit on correlation. A really quick review of correlation. Long story short, we want to see correlation values that are close to 1.0 or maybe negative 1.0. Let's first look at, let me see if I could zoom in a bit. Let's first look at the relationship between win percentage and runs scored. It makes sense in our intuition that if a team scores more runs, they're going to win more games. But what might be surprising is that the correlation value here of about 0.58 is not actually that high. So I wanted to just get that visually in front of us. And once again, if you're curious about how we make the graphs, I left the graph code available on the lecture slides. That is to say, in the relationship, just because a team scores a lot of runs, what I've done here in the colors is to show that they are not guaranteed a playoff spot. On the right side of the screen, you can see that the 2000 Colorado Rockies, a team notorious for their offense, failed to make the playoffs that year. Towards the top left of the scatter plot, you can see the 2014 St. Louis Cardinals actually scored very few runs, so they might have been buoyed by pitching and defense, and yet they were able to squeeze in and grab a playoff spot. Terminally online fans say that the Cardinals have devil magic helping them. Now, let's look at another variable, win percentage, this time versus runs allowed. As you can imagine, the teams that allow more runs tend to win fewer games. So we see a negative correlation, this time of a value of about negative 0.67 there in the top left corner. Now, likewise with offense, it turns out defense alone does not guarantee you success. In this case, does not guarantee you a playoff spot. Towards the left side of the screen, we see the 2014 Seattle Mariners, great pitching and defense compared to most baseball teams in this time frame, and yet they failed to secure a playoff spot. There towards the top right, we see the 1998 Texas Rangers, a great offense team. They probably were a great offense team because their deep pitch and defense were not good in what we see in front of us. If memory serves, the 1998 Texas Rangers included MVP, um, and name just escaped me at the moment. Juan Rodriguez, was it? And also players like Rafael Palmeiro. I probably shouldn't belabor this fact because we probably don't want to necessarily talk about the legacy of those players and how that played out over the next few years after that. Juan Gonzalez. So what I've tried to demonstrate over the past couple of graphs is that it's not enough to think about just offense or just defense. And thus you could imagine what we want to do is think about them simultaneously. We had our mutated variable run differential, literally runs scored minus runs allowed. When we have that as our input variable on the horizontal axis, all of a sudden we are seeing some great results here, a correlation value of about 0.94. In particular, if it's been a while since you've taken your statistics class, you notice that in the scatter plot, the dots in their so-called football shape is much more condensed. We say that there's some evidence of a relationship between win percentage and run differential, while also acknowledging the usual correlation is not causation adage. Thank you for the Zoom chat. Nevertheless, we do see some odd cases. There on the right side of the screen, the 2002 Boston Red Sox, despite having a run differential of almost plus 200 runs, they failed to make the playoffs. And that National League East American League division is quite notorious at times. Whereas towards the middle of the screen, we see the 2023 Miami Marlins. They actually made the playoffs with a negative run differential. And that's a note as well. So we'll dive deeper into analyzing some of these relationships with the tool of linear regression. With a slight departure from the textbook, I went ahead and used the usual statistics notation. So we have our response variable, wins percentage. We have our coefficients, beta naught and beta 1, where beta naught, you'll notice is not being multiplied to a variable, and hence this is called the intercept. Beta 1 is being multiplied by the input of run differential. So we could think of beta 1 as a slope or rate of change. And we math folks like to think of our models having some sort of noise, which we'll just lazily abbreviate epsilon. In R, recall that we could make a linear model using the LM function for linear model. In particular, be sure to put the response variable first, tilde, predictor variable, sometimes called target and feature. And the way we read this off is we're trying to model win percentage explained by the run differential. The only gripe about some of this more old-fashioned coding in the R world, remember when you type out these variable names, at that moment, the software does not know where these variables are coming from. So you have to explicitly state the data frame. There's probably a more tidyverse way of doing this, but I'm just so used to this way of doing things. And in most of these cases, I want to stick close to the textbook. Part of what LM's doing is finding these coefficients for our model, namely beta naught, beta 1. There are two numbers. And we could see that the intercept is given by this number and the slope is given by that number. In ggplot graphics, we could visualize the best fit line using the geom smooth there with method equals lm. I should probably show you the code this time. When we have the ggplot x, y, have a scatter plot, I made them in gray dots. Geom smooth, the software will want you to be explicit with what the formula is, though it's technically not required. And before we dive into more advanced statistics, for now, leave this as LM for linear models. And for today's graphics, I left the standard errors as false to not show up on the graph. So in particular, remember that our relationship or our juxtaposition of win percentage versus run differential had a very high correlation. The scatter plot dots are very close together. And we get a sense that the line that we just drew on the graph to summarize what's going on is doing a pretty good job of expressing that possible relationship. Now, what we could do with that model, I should have kept a copy of the equation on the screen, but I'm talking about the beta naught and beta 1 from before. To interpret those coefficients, we got from the R code, we got beta naught being basically 0.5. What that means is if we plug in 0 into our input variable, a run differential is 0. That is a baseball team that scored just as many runs as they allowed. We get a prediction for the win percent at 50%, which is very good for lining up with our intuition. Over 162 games, this is a baseball team that wins 81 times and loses 81 times. Now for the slope, this is the change in win prediction based on a 1 unit increase in run differential. In particular, if we plug in a run differential of positive 10 wins, we are predicting a team to win about 50.6% of the time. If we multiply that 0.506 by 162 games, we expect that team to win 82 games. And this is a curious point that run differential 10 increased the expectation from 81 to 82, namely increased the expected value by 1 win. I think that brings us to the end of some of the usual statistics. Let me take a pause here and see if there are any questions from the folks in the book club.
I do think it's interesting that the win percentage is such a by itself a strong predictor of playoff. I would have thought there'd be a little bit more noise on that margin, but it was a pretty nice line there. If you get above a certain win percentage, you're probably more likely to make the playoffs. And the little bit of fluctuations at the borderline are not as big as I might have thought, just naively thinking that, hey, there's some guys getting a playoff just by being lucky, it being in a good or bad division, depending on your point of view. Right? But it doesn't happen as much, which I think is good. I'm glad that's not so bad. You don't get unlucky that much, which is good. Play good baseball, you get to the playoffs. I like that. That's my conclusion from that plot that you had.
From there, the folks that are doing the baseball analyses, they of course are being paid to be experts in the field. So the textbook authors now walk us through some of the validation of it all. Now that we have the linear model in place, we want to double check to see if the data is valid and some of our calculations are valid. As you can see in front of us, residuals are the differences between the predictions and the true values. And that's what I have down here. I might have the word switched. To get the predicted win percentage, we actually take the original data from the beginning of the chapter, run it through our linear model again with the very helpful predict function in the R programming universe. With the predictions, compute the residuals. We could look at the residuals here, and I'll explain what we're looking for in a second with the residuals themselves. But talking about the baseball side of things, you get a sense that some teams are very lucky and some teams are more on the opposite side, unlucky when it comes to the performance when being gauged against some of these predictions. So at the top of the screen, I would say that teams like the 2021 Mariners were lucky, whereas teams at the bottom of the screen, teams like the 2006 Cleveland team were unlucky. I have this in table form, which I have here in a GT table. You haven't done a GT table in a while, or just were more curious about that, I've also included the code for some of these GT tables. GT grammar of tables, or great tables, I think it stands for. Great tables are a useful way to organize the information this way. So these are the 6 highlighted dots above. These 3 teams did better in their win percentage compared to the predictions. And these 3 teams were amongst those who did worse in those same categories. On the stats theory side of things, what we're looking for in the linear models and the residuals is that the average of the residual should be 0. And we double check that really quickly. We see that the computer is basically spitting out a very small number that we could treat as 0. Some what are called empirical calculations are helped measured by what's called a root mean squared error. It's a metric that's very similar to standard deviation. So what the textbook authors did here was to double check that amongst the residuals, you can see my description at the top left of the graph, that about 68% of the residuals are within one root mean squared error from the middle, from the mean of the residuals. And about 95% of the residuals were within 2 copies of that root mean squared error, which, if you recall from your statistics class, your teacher, like me, told you something very similar for standard deviation. So far, it looks pretty promising. We had a relationship, or sorry, I keep saying relationship. I just want to be careful. Correlation's not causation. We have this exposition of win percentage versus run differential that had a very high correlation. And we looked at it through the linear regression model and also verified that the residuals are behaving as we think they should be. But there may be some flaws in such an analysis. For example, what about extreme performances? What if there's a team that had a very great run differential? Or, as we were talking about before the recording, what if we have some teams that are intentionally tanking? One thing I wanted to emphasize in from my earlier exposition, should we relate count statistics to a rate statistic? Remember that runs scored and runs allowed, and hence run differential, are all count statistics, but win percentage, as the name implies, is a rate statistic. So it might be kind of odd cognitively to connect those 2 ideas, but for the most part, that's kind of okay. And the data I use for this is seasons from 1998 to 2023, namely the total number of runs and runs allowed from each season. Wouldn't you want a mechanism that you felt more confident in for making predictions during the season. So that's debatable as well. Reading directly from the textbook, Bill James, regarded as godfather of sabermetrics, empirically derived the following nonlinear formula to estimate winning percentage, called the Pythagorean expectation. So as you can see, we're going to estimate the winning percentage, giving this the statistician hat above it, W hat. And Bill James postulated this formula that uses both runs scored and runs allowed, incorporates both offense and defense. Trying out an exponent of 2, this reminds us of the classic Pythagorean formula for right triangles, hence the name Pythagorean formula in our baseball analytics. I sometimes like to remind my students that Bill James did this work in the early 1980s. This was before people had personal computers. So at this point, Bill James might have been working on his handheld calculator. And that might play out in some of the calculations. So we're taking our data frame, tacking on a couple more columns, the formula from above for win percentage coming from the Pythagorean formula, and then a residual from there, the true win percentage minus the win percentage predicted by the Pythagorean formula. For a metric at the moment, we can compute the root mean squared error. And what I like to tell my students at this point is when we're dealing with some metric, we get some number out of it, but we might not know what to do with this number right now, and that's okay. We'll come back to that in just a couple minutes. Now, as the years went on, people kind of wondered about this exponent. Should it be 2? Where did that 2 come from? So let's allow ourselves to remove that assumption a bit. Let's make that exponent arbitrary for a bit and see if we could solve for it. We're trying to predict the win percentage, so we say that it's approximately equal to the true win percentage. With a little bit of algebra, as the textbook suggested, we could get down to this point after taking some logarithms. What this reminds you of in your math classes is the old discussions about slopes and intercepts, or what we had you memorize as y equals mx plus b. If you have an equation in y equals mx plus b, you're assured that you have some relationship that is linear and hence easy to study. We're going to once again treat the left-hand side as our target variable and the right-hand side as our input feature variable, and bring those into the data frame as well. The log win ratio and the log run ratio. Now, this part of the equation does not have an intercept on it. It's just the coefficient k times a variable. So what was surprising to me was putting a 0 here to ignore the intercept term and then focus directly on the log run ratio amongst the inputs. Now, if we're going to skip the intercept, when we ask for the coefficients, we're only going to get the 1. And in particular, in this long-winded discussion, this is figuring out what number k goes in this exponent spot. And we find that it might not be completely the best idea to use the number 2, but instead using numbers such as 1.835. So I revised the data frame to use that new exponent instead. And to justify using that new exponent in the metric root mean squared error, you could scroll up and down and be assured that the root mean squared error did decrease, that we have less error in our model. So what I wanted to do is that, mostly following the textbook's lead, is to get a sense of luck. Which teams outperformed their Pythagorean expectations and which teams did worse in their Pythagorean expectations. For storytelling reasons, the authors focused on the 2011 season. So you might have to go back in your memories a bit. And I went ahead and printed a whole table. And once again, if you're curious about the GT code, I've included it in the slides. But at the 2011 season, the Detroit Tigers, for example, outperformed their Pythagorean expectation by about 6.5 games. And they made the playoffs, but moreover, because their difference was positive, I'm calling them a lucky team. If memory serves correctly, I believe that was the Tigers team that had players such as Max Scherzer, Justin Verlander, and Miguel Cabrera. On the other end of the spectrum, notice that the made playoffs, that's 8 teams, and the other 22 teams missed the playoffs. It's not necessarily true that all the teams that made the playoffs were lucky in the Pythagorean sense. Some of them were actually quite unlucky, such as the New York Yankees that year, 2011. They actually underperformed the Pythagorean by about 4 games, but they made the playoffs anyways. Now, I don't know about you, but my memory about baseball players is not as good thinking back 14 years. So I just reran the code for the 2023 season about 2 years ago. At the top of the list, the Miami Marlins outperformed their Pythagorean expectation by about 9 wins. And I showed you earlier that they made the playoffs. Right behind them were the much celebrated Baltimore Orioles, outperformed the Pythagoreans by 7 wins, made the playoffs, and this is part of a long rebuild process that they did. However, some of their internal business or analytics folks probably realized that maybe they were overperforming, and that's why they might have justified some of their arguably financially conservative motions or proclivities when it comes to deciding which players to sign and which players to retain. At the very bottom of this list, coming from the 2023 season, which teams were the most unlucky? At the very bottom were the San Diego Padres, underperformed the Pythagorean by 10 games. And despite their recent success overall, that's the year the Padres missed the playoffs. I'm going to go ahead and take another pause here, welcome in questions or commentary from the folks in the booklet.
Well, 9 or 10 wins, that seems like a lot to be lucky or unlucky for.
So while the Pythagorean formulas, whether it's the exponent of 2 or my update was the exponent of about 1.835, there's still some cause for concern about why it might not be completely good at modeling win percentage. So we're going to look at some quick case studies as suggested by the textbook authors. I'm following the material pretty closely here. They grabbed some retro sheet data from the year 2011, going to focus on the Boston Red Sox team that year, and we'll mention why in case you've forgotten in just a bit. But in particular, I want to point out that when you're working with a more complicated data set like retro sheet, this tends to be separated between home and visiting team. So you have to really keep track of which stats go with the home team, which stats go with the visiting team. And here you can see that we compute a score differential, but it has to keep track of Boston's at home or away, which reverses the subtraction if need be. Otherwise, just keep track of whether or not the Red Sox won or lost the game. So I decided to use a density plot to express that season, the 2011 Boston Red Sox, the score difference on a horizontal and overall a density plot. I also geeked out a bit and tried to give them the official Boston Red Sox colors as well. Now, if you don't read density plots as often as I do, we'll go ahead and read off the caption at the bottom of the page. The 2011 Red Sox had victories decided by a larger margin than their losses. So when they won by 4.3 runs on average. But when they lost by 3.5 runs on average. And this is part of the reason why they underperformed in their Pythagorean prediction. Another thing to think about, which I'm just going to haphazardly call clutch performance, is tracking performance in games won was a difference of just 1 run. We call these 1-run wins. And back in that 2011 season, we see that, first of all, I once again put the color codes that if they outperform the Pythagorean, I have them in the dark blue. And if they underperform the Pythagorean, I have them in the gray. We see that in the top right, the San Francisco Giants had many 1-run games and many 1-run victories. And as you could expect, that ended up adding up to how they outperformed a Pythagorean. In particular, we call that in baseball, if you win by 1 run, that's 1 win. If you win by, say, 10 runs, that still only counts as 1 win. So we're only counting wins here, and that's part of what's going on in this formulation. On the bottom left of the screen, we once again see the unfortunate Boston Red Sox had very few 1-run wins, partly because they usually won by a lot, but partly because they sometimes lost those games as well, and they had underperformed the Pythagorean. And folks who follow baseball, and as the textbook implies, would point out that's the season where Boston actually lost their playoff spot in a late light of a very classic playoff chase, and where Tampa Bay actually squeezed in and got that playoff spot. And thank you for the link in the Zoom. Fortunately, I'm not a fan of either team, so it didn't matter to me. Another investigation that the textbook authors implied, they called this top closers, but these days we might not think about every single pitcher pitching at the end of the games as a closer. So I decided to broaden this and just call them great relievers instead. We're looking at games recorded being above 50. So pitchers that tended to be used fairly often, and an earned run average of less than 2.5, which is a fairly low bar these days that only a few great relievers can achieve. When we do a few calculations, look at the Pythagorean residuals, we see mostly positive numbers coming from that. It might not mean much right there, but if you take that average and multiply it by 162 game season, a team with great relievers are eking out about 1.3 more wins. That number might be subjective. Some teams are probably using that to justify paying their relievers less money, but some teams are out there paying their relief pitchers a lot of money. So that could yield further discussion. Let me see where we're at. I'm in the last section of the chapter, and I did a couple of the exercises as well. One question we could ask ourselves is a old adage from baseball scouts: how many runs for a win? And around this time, in the early sabermetrics, or maybe earlier in baseball scouting in general, there was a rule of thumb saying that 10 wins equals 1 win. And we saw that earlier with the linear regression models, in particular this one, talk about run differential and win percentage. And that's what we did when we plugged in the numbers. If we plugged in a run differential of positive 10, we got 1 more win out of it. So to not necessarily criticize, but to go deeper into the Pythagorean formula, Ralph Calda derived the number of extra runs needed to get an extra win in a more rigorous way using calculus. Apologies, my mouth is stumbling across the R and W sounds quite frequently here. Just for the sake of making the math a little easier on me, I went back to the exponent of 2, but you notice that we're also taking the number of games played into account. We're going to find the rate of change in the wins with respect to runs. And since runs appears in both the numerator and denominator, you recall your wonderful adventures in calculus class, do some quotient rule, and you eventually end up with this formula. The textbook authors did not bother to use printed space under textbook for this either, but it was neat that they did point out that for calculus at this level, you can do this in R with some symbolic calculations. So you could get the formula for the derivative, but at least from what was presented, it does not simplify the formula for you. Taking the reciprocal of that formula, we could think about this as incremental runs per win. If we then think about runs scored and runs allowed as rate statistics, that is per game, we don't have to worry about this games variable at that point. We can make a custom function in R to deal with that. So this, of course, relates to the rest of this formula. And recall that anything up here right after function are the default values. If the user doesn't plug in anything explicitly, we're assuming a game where there are 5 runs scored and assuming that they also allowed 5 runs. What I found pretty neat is that you could do a grid search to plug in many different numbers. I departed from the textbook here. I didn't really feel the need to plug in fake values such as 2.5 runs scored. I decided to use whole numbers going from 1 to 7. We could expand grid on that to get 49 permutations. Apply the IR function from above to all 49 of those permutations, and then pivot wider to be able to show this in a nice table. If you look at the left side of the screen, at 5 runs, and the top of the table at runs allowed being 5 as well, it does predict that 10 more runs would need to be scored to get a win in some sense. But what this table also shows us is in the top left, if you have a low scoring game, such as a 1-1 game, then scoring 2 runs in some sense might give you confidence that you're going to win the game. However, if you have a high scoring affair, maybe 7 versus 7, and you don't really have much confidence in the way the game might turn out, you might have to score 14 runs to have confidence that you would win the game. And then there are some edge cases as well. As an aside, I was afraid that when I ran the GT colors on this, I might have to take a logarithm to get the colors to work out correctly. But the color palette actually did this job automatically without me having to worry about any more rescaling. Now, I did a couple of the exercises so I could fill out more of the time, but let me take one more pause here because we are at the end of the chapter. How are we doing, folks? Any questions, discussion?
No, great job so far.
Okay, so let's go ahead and move into some of the exercises. There were 4 of them. I did 2 of them. The first one is about the relationship between winning percentage and run differential, but across the decades. of baseball data. Long story short, the baseball data goes back to about the 1870s, and in this Lawman data table goes up to the year 2023. So what we're going to do is look at the linear regression models like before, and the textbook recommended going over these 5 decades. From there, with the linear regression models, the equations, we're going to plug in a run differential of positive 10 just to see how that plays out in each time frame, in each decade as well. I was kind of surprised that the authors only asked for these 5 decades. So me being a masochist, I decided to just do all the decades. And egg on my face, it turned out that the answer is basically the same throughout each decade. So plugging in a run differential of 10 runs into the linear model for each decade yielded about a 50.6 win percentage, which is actually reassuring. That means that the models that we are employing here in the early sabermetrics are also applying, at least from my exploration here, over the past 100 years or so. Oh yeah, this one is fun. Take the Pythagorean results and take them back to the 1800s, the 19th century. As baseball was evolving into its final form, 19th century leagues often featured abysmal teams that did not even succeed in finishing their season, as well as some dominant clubs. We're going to fit a Pythagorean model to the run differential win-loss data for teams that played in the 19th century, the 1800s. And then we'll do a little bit of exploration of the results from there. The Bill James first draft of the Pythagorean formula had an exponent of 2. When I looked at the data from the year 98 to 2023, the exponent was about 1.835. And when I looked at the data from about 1871 to 1899, the exponent is about 1.931. So a little bit higher for the exponent. What I did from there was I looked at as recommended by the problem, I looked at the best 10 teams from the 19th century according to win percentage. Let me zoom in for us. There we go. So by win percentage, the best team back then were the 1875 Boston Red Sox, having won nearly 90% of their games. In comparison, the best team over this century, I believe, won about 71% of their games. So these teams all did relatively better than that. And you see some classic teams there. Shout out to the Providence Grays. While we're here, if you go back to these notes, you might also want to get a sense of runs scored per game and runs allowed per game to get a sense of what baseball was like back then. Now, admittedly, with the 3-letter abbreviations that we saw earlier in the presentation, I did not understand them all going back for some of these older teams. So what I did in the Lawman data tables was there's, in addition to the teams table, there's also a table called teams franchise. I merged those tables together. And instead of showing the 3-letter abbreviation, I wanted the full franchise name to make it a little easier to describe what's going on. Finally, on the right side of the screen, we once again are getting a sense of which teams outperformed their Pythagorean expectation based on the run differential, based on the runs scored, runs allowed. And in terms of these top 10 teams from that century, 7 out of the 10 outperformed their Pythagorean. So that's why I'm calling them lucky. And then finally, out of morbid curiosity, let's look at the worst teams from the 1800s. You'll notice that the Washington Nationals of 1872 and the Baltimore Marylands scored 0 runs. You might recall one of the formulas that we came across actually had a logarithm. When you take the log of 0, it breaks your calculations. So I took some liberties at this point. On the right-hand side of the screen, you notice on the residuals, in terms of comparing the Pythagorean with their actual win percentage, 9 out of the 10 teams were unlucky. And then finally, let's just enjoy some of these franchises that we do have some records of back then. The Brooklyn Atlantics, the Keokuk Westerns, the Elizabeth Resolutes, the Brooklyn Eckfords, the Wilmington Quicksteps, the Cincinnati Reds, the Philadelphia Centennials, and yes, we are highlighting the infamous Cleveland Spiders, who have 134 wins that year in their notoriety. And you probably heard about that recently if you've been keeping track of the recent White Sox and Rockies teams.